I started in undergraduate school in 1977, and I considered that was the start of when I became a chemist. Although, if you talk to my parents, I managed to stink up the basement quite a bit well before that. So I've been doing chemistry for quite a while. There have been a number of highlights. I think one was very early on in my career at OSU. We were working on a mechanistic problem, and somebody had asked me whether I knew anything about the thermodynamics of the reaction. So, we decided to tackle that and engineer a part of the reaction that would shift where the equilibrium lie. And I did one experiment, saw a color change in the tube, and I knew right away at that point, it was like a door opening up in front of me, that I had the tools and everything I needed to really make a fundamental advance in the problem. And that was very gratifying. Well, we've been looking at the ways in which metal atoms or metal complexes mediate the formation and cleavage of carbon-oxygen bonds. And in thinking about different ways that we could apply that, it occurred to me that most of the development of this chemistry was an effort to put oxygen into compounds that were coming from petroleum, things that are made of mostly of carbon and hydrogen. As petroleum becomes a scarcer resource, we have to look for other feedstocks, and biomass has actually the opposite problem. Biomass is largely composed of carbohydrates, which have a lot of carbon-oxygen bonds. And so we want to use some of the chemistry that we've developed to try and break those carbon-oxygen bonds selectively and convert biomass into other useful commodity chemicals. For the non-scientist, well, is most of the things around us, that we use in day-to-day life, are made from petroleum-based compounds. And as fossil fuels become scarcer, harder to get, more expensive, biomass becomes an attractive alternative, as well as being greener and better in terms of its carbon balance. So essentially, what we're trying to do is to use resources that nature is giving us to make things that we want to use for everyday applications. It's difficult. I've always been a work hard, play hard kind of person. When I started, the typical image of an assistant professor is somebody who, works 80, 100 hours a week or more, lives, breathes, and sleeps research. And I decided pretty early on that while I was going to give work my full effort, there's a limit to what I was going to do there. So I always made sure to take a day a week and go hiking or go skiing or doing something for fun. Now I've got a fiance who keeps me in check, and so she makes sure that I have my priorities where they need to be. It's an incredible honor, particularly when I look at the names on the list of, the 98 other people who were announced this year. These are all people that I highly respect, I know by reputation, and who have made incredible contributions, both in terms of the science that they've done, but in terms of the other contributions they've made, both to chemistry as a profession and to the society. and I take it as an honor that the things that I've done, both in my scientific research career, with my teaching, and with my service to the university and to the profession, are viewed in that kind of framework.